So, this very short presentation deals with MRI images of the heart, and this is work that I was doing back in 2010, just after I'd finished my PhD. My PhD basically dealt with two-dimensional, three-dimensional data of the brain, and trying to model that using all sorts of modeling techniques that do derive the statistics of the brain structure. In this case, we're also dealing with the dimension of time, so hence we've got a four-dimensional problem essentially. Now, the goal we're trying to address here is a survey identification of the abnormalities, things like the stroke, for example, or people that have a certain tendency to have strokes. What this actually necessitates, in essence, is a sort of a very concise representation of vast amounts of information. Not only the sequence of the data, something which conveys the motion of the data, but also something that will have a finite number of points. So what the image basically shows is a bunch of arrows overlaid at the corners or the edges of the chambers. And these are essentially the points of interest, and they also tell you more about the way things change over time as the cardiac cycle, that is the heart beating, and the heart, being a muscle, is going to have this kind of a two-phase motion, expanding and contracting. And these type of errors basically tell you which part of the cycle it's in. What you then want to do is to get a sort of a decomposition of all that, and a sort of a subset of all this data that you have in a four-dimensional space. And you want to reduce that in a meaningful way, which still retains the data of interest to you. The data itself is just standard, 3D MRI data. And this data is extracted in a very consistent fashion with a 3 Tesla scanner from different individuals, from different subjects or patients, depending on their condition. and and basically, by adding tag into the data, you can vary the amount of data that's attenuated through the tissue. By doing that, you can be a bit more selective in what kind of signal you take from which type of organs, and how you distinguish from one part of an organ from, how you can distinguish parts of the organ that are of interest and those that are not of interest. The tagging essentially would put a sort of black lines along the data, and as the signal dissipates a bit and you carry on taking more and more frames of the data in very low resolution, you will still get quite a bit of the signal left, and you'll be able to tell which structures of the data are still moving and in which way. So the tagging itself gives a bit more of a structural orientation. As for the methods, it's a combination of things, really. I mean, you've got edge detection as the core, especially trying to find the initial positions to work with. And then you've got means by which you're going to track those edges as the frames go on and on. If you want to take some finite sampling of points at the end along the edge and make these values also discrete, then that's going to require that you also know how to find the edges of interest. For example, certain corners or certain types of the parts of the heart, when you try to calibrate the hearts and to normalize and to adjust things such that you will pick the analogous points in different images. Once you've done that, and you've done it correctly, you will be able to then pass it on to a meaningful process of principal component analysis. It's a statistical tool of dimensionality reduction, and once you've developed a set of models, you'll be able to match any given image to a set of models and say something about a similarity. based upon the similarity, you'll be able to say something about the characteristics of the image, which, if the model you fit it to is a model of people with some kind of atrophy, you'll be able to then generalize it to say that perhaps the image you deal with is exhibiting some kind of abnormality as well. As for the edge detection, well, we basically investigate a bunch of them. Things like the very classic canny edge detection, or even on-off-the-shelf kernel filter kernel, like Sobel. But then what you also want to do is to do some kind of an analysis to try and distinguish the different performance you get from that you would attain by default by not setting things correctly, such as the thresholds, and that requires a bit of offline studying of how to best adjust these values to get the maximal performance at the end. The preliminary outliers and the preliminary issues with trying to fit the data are quite important to resolve. You do want to ensure all the points are laid in the correct corners of the heart near the chambers. Once you've done that, you can use a servo template to ensure that you don't deviate too much from what you had to begin with. That is to say, you don't really want to move the points along the edges in a way that would be kind of nonsensical if you kind of have some awareness of what a heart is supposed to look like. And by doing that, you can stay along the lines of kind of sane edges on the heart and track it quite correctly. Now, as for staying along the edges, you can also use a bit more data which is related to the pulse and the cardiac cycle. So, except for the intensity, which is pretty useful on its own, you might want to use something like the neighboring points. Assuming things move in harmony, you might be able to say, oh, the neighboring points will be expanding, so therefore, I know this point that's adjacent to it is going to expand as well in pretty much the same direction. And taking into account, of course, the pulse cycle itself, you know whether the heart is expanding or not, and you'll know if it's supposed to move in a certain direction or not. So, taking into account all of these factors, you can kind of say that a certain direction of movement, or a certain movement and shift in the edges is most likely to be the correct one based on the anatomy. Now, once you've done all that, you want to quantize, you want to normalize, you want to calibrate all those different factors. So you generally want to ensure that in terms of the cardiac cycle, you get things in alignment, so you compare like with like, but also in terms of geometric things, you want to ensure that the scale and the orientation in the image is all alike in all the images you deal with. Once you've done that and you've got consistent values collected, you can concatenate them and get a kind of a vectorized form. So for each image or for each sequence of images, you get some kind of a very concise representation to be used. Now, why would you want to do that? Well, principal component analysis relies upon you having a consistent markup of the data. And, if you've processed everything very concisely, if everything is very well aligned, and if you removed all the calibration errors associated with the sequences of the heart not being in alignment in terms of the cardiac cycle, then you will be able to get the statistics out of it quite correctly, and they will characterize the interpersonal traits and not so much the intrapersonal traits, and they will not be made noisy by all kinds of factors that are to do with the inaccuracies in trying to mark up the data. Then you can build parameterized models by which you can represent the pertinent images. You can reconstruct the images, the pertinent images in 4D. Really, if you know the values of the parameters for each one of them based upon the models you build. PCA, is kind of beyond the scope of this kind of very short presentation, so I'm not going to go into it. But the important thing is that then you have some kind of a comparison of the similarity metric by which you can tell how similar a given image is, or a sequence of image, to a particular group. If you have a particular group, for example, from people who have stroke and one for normals, then you might be able to say, based on the 4D sequence, after a long process, if it fits one group or another. And that's the sort of process that kind of sums up the thing. What you want to eventually have is a process by which, given an image, you can take it in a certain frame of reference. You can normalize it in some type of way, and then you can compare it to a set of models, and you can find which models it fits the best. If you know which group of images it fits the best, or which model built from a group it fits the best, then you will be able to generalize it and say this image pretty much exhibits the same traits as those ones, which may, say something about the group based upon the statistics and the metadata you took. Now, the nice thing is that, as long as you're consistent in your processing of data, as long as you're doing things in a very accurate way, the markup of the data, you will be able to get a very purely, data-driven method of trying to classify images and to say something about them in an autonomous fashion.